So today we'll talk about engineering solutions. The objectives of this chapter would be, firstly, we need to recognize the importance of engineering problem analysis. We need as well to explain the engineering method. Last time we talked about the design process steps. Today we'll talk a little bit about an engineering method, steps to the engineering method, how we're going to apply that, where it is important, and so on. Then we'll apply general guideline for problem solving and develop the ability to solve present simple or complex problems in a logic or a systematic way. As introduction, the practice of engineering would involve the application of your accumulated knowledge that you accumulated through your studies and your experience that you get either through your co-op or through the industry and so on. As well, you're expected as an engineer of practice to apply the fundamentals of engineering. That would include the design and problem solving. Then you would be able to approach, analyze, and solve technical problems intelligently and efficiently. Now, for problem analysis, as a qualified engineer, we expect certain characteristics out of you. One of those characteristics is the ability to solve technical problems. And you need to know that problem solving is a combination of art and science. Why we say art and science? For two things. Firstly, we need to identify what is the meaning of science, what's the meaning of art. Now, science is the knowledge of the principles of mathematics, physics, mechanics, and chemistry, while the art is the proper judgment, your common sense, your experience, and your know-how knowledge that you gain along the years, so that you use it to reduce the real-life problems by matching design with application. So they call it, when you look at the patent, there's a section called state of the art. It means what kind of novelty in that patent, what's new that you're bringing in with your patent that's going to help humanity and so on. So that's part of it. The other part, I would say, it is the art, what came in your mind. Like as an engineer, you are an artist, or in a way or another, you are doing a machine. When you buy your car, it has an art into it. There's a beauty into it. So you can see here, we have something, they call it concept art. It's been designed by, I can't read his name. So I believe this is back to a sci-fi movie, but Tron, exactly. So the concept art here, you are designing a mechanical machine. Maybe it could be futuristic in this case, like we didn't see it in the road today, but it should make sense. You can't just draw kind of a weird machine that will never work. Although sometimes it happens in the market that you design something, then the industry would say, hey, it's impossible to make that happen. So here you can identify wheels, you could have a powertrain, engine, and there's a seat, then the driver would be hidden somehow within the machine. So you can see it's a beautiful piece of art. I can take this and put it in my living room and still looks good, right? In case you're interested in machines. So there is art behind it. You can't split engineering from art. Art is the beautiful word of design. When you design, you need to design something beautiful so that it will be an art. And of course, the other portion of what does art means, it is the know-how, the experience, the judgment, and the common sense for an engineer. Now you can see here how the concept goes when you have a certain analysis or you want to come up with a design. We will stick with the same product that we mentioned first. So here, maybe you'll start with some hand sketches, do circles, do some curves. So you had a general idea about the concept of the machine. Then you go to your CAD or 3D design software and try to make that minimized or that simplified sketch into a real, or let's say a 3D well-done design. So you start designing the wheels, how the shell is looking like, how things are moving together, where you're going to allocate the engine, where you're going to allocate the transmission, the wheels, and so on. So that's how you move from an idea. We talked before about the design steps. One of them is visualize or conceptualize. So you want to be able to go from sketch into a real-life product. Now you can see here, let's say you did rendering in SolidWorks. So you designed the product in 3D format. and you know the dimensions of the wheels, you know the wheelbase of the machine, you know what power is expected out of this machine, where the driver is gonna sit, and all of that. Now you say, okay, I'm ready to do a rendering. How would it look like in real life? This is not real life yet, but it's a rendering. Like you can use SolidWorks to design a certain box, then you do rendering, then the box will look like as close to reality as possible. It takes a lot of processing power out of the PC to be able to make it look as realistic as possible. Sometimes those images are used for marketing. Maybe this product is your idea for some startup company that you made, and you gotta propose that to the investors. So you're gonna make it look nice, as realistic as possible, and it makes sense as much as possible, you know, to get the attention so that people get the idea, what's this machine, what does it do, and so on. Now we will make it a reality and go out there to the test track and put some professional person and do testing on that machine. Like we put the engine together, transmission, wheels, and all of that. We think it looks good, it runs. Now we want to see, is it usable on the roads of the country that we're targeting? Then you put somebody who's professional inside of it, who knows how to drive and test. Maybe you plug in some of your sensory, a laptop to it, and be able to see what's the output torque, what's the horsepower, what's the maneuvering, what's the G force, and all of that, to be able to tell how good is this machine, and can an average person drive it, or need to be a personalized person who have a certain certificates and so on. Now then, after that, you would take it to the road, give it to, let's say, the early adopters, the people who felt excited about the idea, and they paid the money, they hop in, and they start using the road. Maybe now you see in the market the Hummer EV. Few people have the money to buy it. They are excited about the concept of a Hummer EV, electric-based Hummer vehicle. They have the money for it. They're considered early adopters, so they take it, they do off-roading with it, they see if it can last or need a charge, and so on. So they could be these people. Now let's take an example. Now we have two specialized people. The first one is a manufacturing engineer, and the other one is a logistics specialist. They're working for a large electronics company, and they're given the task to decide whether it is recommended to introduce a new computer that focuses on CAD market in terms of profitability. Now, working models of the computer are already created by the design group, and the estimated price is determined by the marketing department. Now, the engineer and the specialist need to determine the cost of the assembly and distribution and the product profit afterward. Now, I don't know if you got it already. So there's an engineer and specialist. What's the difference between engineer and specialist? Maybe a specialist is somebody who got a diploma in the field. So it's called specialist. In this case, logistics specialist. Maybe somebody who have diploma, but he been in the company 5-10 years. So he been kind of elevated specialist who's like managing the other specialists. So this guy, logistics specialist in manufacturing, like let's say in the factory, there's something called logistics. It means, do I have the machines needed to be able to produce a certain part, or do I need more inventory? Let's say it's a company of electronics. If they're making a PC, then the logistics specialist take care of all the logistics, which means, do we have enough boards to build all the keyboards? Do we have enough boards to build all the mouses? Do we have enough boards to build the screen? Do we have the right type of glass or plastic? Do we have the right amount of hinges and all of that? So that's the definition of logistics specialist. It's kind of a question marked position, but that's the design for it, or let's say the explanation of it. Now, manufacturing engineer usually is somebody who's in the manufacturing plan. Let's say, again, it's a PCE production company. They have production lines where they assemble all those PCs together over and over again. They make 100,000 pieces a day. So the engineer overlook the process, make sure they produce enough of what they want, make sure everything is working, the machines are working as they're supposed to be, and all the technicians and specialists are doing their job. Now, in this case, they have an idea. They want to design a PC, like there's a gaming PC. They want to design a PC which focuses on CAD market. They want to see, is it profitable to do that? Like a PC who can handle SolidWorks, CATIA, and all other design software, so that they sell it to the companies who do a lot of designs. So that's the whole point of this question. Now they want to decide, they know already that the design, how the PC look like, is already designed by the design group. And the price expected for that PC is determined by the marketing department. Now, what does the engineer specialist need to do here? They need to know the cost of the assembly and the distribution of the product. So they want to focus on the manufacturing side of the problem. Now let's go with both sides. Firstly, we go with the science side, then we go with the art side. Now for the science side, engineering economy is defined as used to find the cost factors and time frame. So to be able to calculate the cost and how long it takes, already there is engineering economy concepts that can be used to find those factors. Now when the production and distribution methods are established, then the cost can be computed using standard methods. So what they need to do in the science side, they need to establish the right production and distribution methods. Either they need to choose or they build new methods for production and distribution for the new PC. Now for the art side, the selection of the production and distribution methods depend heavily on the experience of the engineer and the specialist. They need experience, common sense, and good judgment to be able to solve the art side of the problem for this product. Like, you know, by science side, I know how to calculate the cost. I know how to calculate what methods I need to follow to be able to deliver the product in the industry or in the manufacturing facility. But for the art side, that's like your common sense. Do you think this works or no? Instead of buying a lot of machines or developing new methods that you know already doesn't work by experience. So you can just skip that and go to what works exactly in the market. Now, when you are assigned a task, you need to ask certain important questions. Questions to be asked in this case, now you need to ask whoever dropped that problem on you, how important is my answer to this problem? That's first, like, is it a big problem, small problem, or doesn't matter? We need to ask you anyway, so your answer doesn't matter so much in the next process. Then would a quick solution or a surface simplified solution be enough? Or you guys need a high accuracy solution? Like somebody would tell you, hey, we need a new PC. Okay, go ahead to Amazon and buy a new PC. What's the problem? You know, you can do that, but maybe they say, no, that's not what they're looking for. We need a PC which have a certain processing power who can, let's say, manage the whole production line of the factory. Then in this case, need to be more accurate in terms of answers and finding the solution. Now, I need to ask as well, how much time do I have to solve my problem? Like, you give me a problem, go Jordan and solve the problem for us. Then do you need to solve it today by the evening, or you want it to be tomorrow, next week, next month, and so on. Then I need to know as well what resources are available to be able to use in solving this problem. Do I have, let's say, an archive of similar problems that you guys have, what they call it as lesson learned in the market? If they have, I can look at them and see which one is similar and how did they approach it to solve the problem. If not, then other resources could be somebody who's more experienced than me. It could be a software. It could be money budget. Maybe I can hire an outsourced company who can help me solving the problem or portion of the problem. So you need to know your resources. Then you would say, am I the only one working on the problem, or am I a part of a team? Like, is it only Jordan who's working on the problem to solve it, or it is a group of people? Let's say, in this case, the manufacturing department, there is maybe 50 manufacturing engineers like you who are working on the problem, and they can help you out. Everybody take a portion and solve the whole problem. Then I would ask as well, how good is the problem defined? Is it well-defined problem, or do I need to work on researching the problem and define it better? Then do I need to collect more data about the problem, or the data has already been collected and the problem is well-defined? Now for complex problems, you ask the same previous questions, but you add to them more deeper level of questions. Like you would say, what theory am I expected to use in my solution? Is there a theory being defined, or I want to create my new theory to solve the problem? Then I would say, is this problem first time arise, or first time somebody is attempting to solve it? Is it a novel problem? In this case, we're talking problem could be in research, like somebody trying to solve how to use the nuclear power at home safely. Nobody ever did that before. Then you want to look for a novel solution for this, Then, do we understand the theory, or we need time in research, review, and learning? They would say, oh, everything has been set up. We've been researching this. We funded $100 million into this research, and we know it very well. Let's say the cancer problem. Like until today, we didn't have a cure for cancer. Then there's a lot of research, a lot of money being spent there. So it's a well-defined problem. We know what's the problem, but we don't know what's the solution. We understand what theory, what approach that we can follow to try to get near to the solution, but we don't know it exactly. Then can I make assumptions in my solutions? Like in the guys who are in the factory, the engineer and the specialist, now they want to make the production line and distribution as it should be. Then I would assume in this case as an engineer that there is already enough budget or enough money to do whatever I want. I assume that. Could be wrong, like, hey, no, you have $100,000 to use to solve the problem. But without that, I would assume I have as much money as I want, so I can just import and solve the problem. Then are my assumptions valid or applicable? Like I'm saying, okay, I have unlimited budget, which is not realistic. Then I would go back to the manager or to the company CEO and say, hey, I have a solution, but it's going to cost you $1 million. Then he's going to say, oh, no, why you assume that? No, we have a limited budget for this problem. So that kind of thinking approach that you're going to follow. Now, something else called the art of problem solving. Now, in the market, there is many approaches that are called art of problem solving. It's not only one art. One of them is following those steps that we're going to talk about. But there is things that you're going to hear a lot in the market, especially in the mechanical engineering industry, which is called root cause analysis. We're going to talk a little bit as moving forward. Root cause analysis is a way or a certain art of problem solving, a certain approach to solve a problem in a certain way. There's as well design review based on failure mode that is being used by Toyota in specific. Like Toyota company, they use something called design review based on failure mode. When they have a problem in one of their vehicles, they follow that, and that's a very successful science that everybody should know, even though they keep it secret. But me working there, I try to write and make lectures about it to get the word out and get it populated as much as I can. So we had root cause analysis, we had the general art of problem solving, we had design review based on failure mode, or they call it DRBFM. We had something called FMEA used by Ford and General Motors and the American companies in general. Like those are all art of problem solving. We can maybe in future courses talk about them more. Now, the steps for the art of problem solving, you need to know first that the problem solving is a skill that you develop with experience and practice. You need to have, while solving the problem, a balance between time and resources, and you need to be able to obtain accurate and valid solution. Solution only is not enough. You need to have accurate and valid solution that you and your company trust. Then you apply the engineering method. Now, the engineering method steps or design steps for engineering method are the art of problem solving that we're going to see in the next slide. Now, for the engineering method, you can remember now the design process steps. They are similar somehow, but here you are using engineering to solve a certain problem and follow the problem from its source all the way to the solution and documentation. But it's very similar, but it's not the same. So first, what you're expected to do, you need to understand the problem. We talked before, like you have a problem, understand it, how good you understand the problem, then collect data, probably that's familiar to you. Collect as much data as you can about the problem. Then you need to select the appropriate theory or principle to approach your solution or to do the solution. Then after that, you do the necessary assumptions that are needed. There is no problem without assumptions. Not every problem is well defined all around. You gotta assume some stuff, but make sense in your assumption, not to ruin your answer will be not logistic or not logic at all. Then you need to actually solve the problem. Eventually, you need to verify and check the results. You can imagine the engineering method as you are solving your physics class problem. You follow the same approach even though you don't realize that. But we're talking here about more physical real-life problem that you can use the same approach to solve a real-life problem at the same time. Now we'll talk a little bit about common sense. When I tell you your solution needs to be common sense, your thinking needs to be common sense, it's a very generalized, unmeasured term. Everybody sense what he thinks is common sense could be ridiculous for somebody else. But there is something that most of engineers agree on. I would call it the engineering common sense. Like in this case, let's say you took a loan to launch your startup company. The loan amount is $5,000 to be paid over 12 months period with an annual interest rate of 12%. Now, the question is saying, what is your monthly payments to close the loan by the end of the year? Let's say you did your calculation, your answer was $12,000 a month. The bank is very, very happy about your calculation and he say, good job, thank you. But in reality, you took $5,000 loan, how come you're gonna pay $12,000 a month? Of course, it doesn't make sense. So when I say common sense, that's just to clarify the common sense. When I say common sense, you combine the facts and you think the outcome doesn't make sense at all. Like there's no logical sense. No bank will let you pay $12,000 a month for a $5,000 loan. I would say common sense in a more philosophical way of explaining that is comparing your past experience with your current results. So if past is way different than current results, then you'll be surprised. Like let's say driving a car, when you steer the car, it's gonna steer smoothly and life is good. Let's say you had a junky car, then you steer to the right, then it's go left, and you say, whoa, 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 that doesn't make sense, So you lost your common sense because you connect with your memory, car should go smoothly to the right as I intended to. If it go left, then something else I'm not aware of or it surprised me. Now you need to present your problem in front of the right audience. So you follow the engineering method for problem solving. Now it is time for you to properly present your problem to the right audience through either in-person presentation or through cold presentation or documentation, or maybe other means of message delivery. Maybe you are just FaceTiming with some CEO of a certain company, and you're gonna just show him what's your solution for his problem, and you're proposing your startup solution that you're building your company around, and still you present something to him. Could be like what I'm doing now, presenting data show, could be presenting over the internet through Microsoft Teams, whatever it is. But you need first, before problem presentation, make sure your solution makes sense. Then try to make it as appealing, as nice as possible, and still professional in the same way. You don't want to put some content that doesn't make sense. And you need to present the problem properly first and to the right audience. So let's say you are a CEO of a startup company that you started last year. You want to go present in front of investors. It makes sense to wear properly so that they will gain your trust. They're going to put the money with you. You better be a good presentation for the company. Otherwise, send somebody else. You can't go, like in a beach clothes, for example. You can, but it's not appropriate for that thing. Then same thing as the presentation language. You need to be, let's say with investors, you need to be precise. You need to show numbers, graphs, and be right to the point. Don't waste time, and so on. Then documentation. In case of a company or an employee in a company, you need to document your solution and propose, or let's say describe, why do you think this is the good solution for the problem. Now, for problem presentation, there is steps that you can follow while you're writing in your Word document your problem presentation. In each form you want to choose, they're gonna be following this kind of approach. Firstly, you have the problem statement. In a statement, abbreviated, what is the problem exactly? Then you need to use a diagram whenever possible to be able to tell them what is the problem and what is the approaches that you think, alternative solution that could be a solution to the problem, why you think this is better, why this is worse, and so on. Then we use the theory. To solve this physical problem, I'm gonna use, I don't know, maybe I need to use the motion equations in physics. So that's your theory that you're using. Theory not necessarily like related to math or physics, could be like any other theory. Like there's certain diagrams in vibration we used to use in the market while we're working with Ford and GM. They call them Campbell diagrams. Those diagrams, they show you vibration. Remember I told in MATLAB, They show you vibration in a waterfall style, so he will tell you when the vibration is good and bad. So your theory in that case is Campbell diagrams. Then you do the right assumptions and you write them down, and why you think they're good assumptions. The more you write, the better in company environment. But I would say when you are a startup company, different story. But here we are talking about as an employee in a company. Then we talk about solution steps, how you're going to approach your solution, how you're going to execute it, all the details needed. Then you identify the results and verify accuracy, so you can say solution check or solution verification, solution validation. You need to put a headline, then you move forward. Then eventually conclusions or discussion. This way, whoever read your document, he see it's a well-written document. Everything has been specified under a certain headline. Maybe you have a table of content for the thing. If it's a PDF, if you click on a certain content, he's going to take it to it. All those things are a good way of documenting the problem and solution. So we have an example here, tap water impurity. Residents of a certain state are complaining about the taste and quality of the tap water that the city provides. Some of them experiencing liver problem that they think due to impurity of the water they drink. So that's the problem. Problem statement, tell me.
Impurity of water impurity.
Let's see, impure. We don't want to write a lot, but yeah. Diagram. I would say we show water, healthy water charts maybe here, so you can use it in your presentation, and where we are versus where we are. Theory, what theory you're using here? PPM, testing, principles, right? Assumptions, we already did assumptions. Water is already filtered. Solution steps, I think we did that previously, right? Yeah, it's similar but different. Solution steps, in case you went with the solution of applying filters, we could say first provide, secure the right budget, right? Then you would say after that, secure the right budget, then buy the filtering system from the right company, and before that maybe you need to know how many homes you have, and you can go on and on and on. You get the idea. Identify the results. We said we retest the water and assist as needed. Of course, in your homework or exam, I wouldn't accept those answers, but just here for the sake of time. Conclusions, blah, blah, blah. You can write whatever you want. You got a problem. You have a tank to be constructed. He will hold 5 by 10 to the power of 5 liters when filled. That's how much volume it has, like 500,000 liters of water. The shape is to be cylindrical with a hemispherical top. Hopefully you can imagine that. Cost to construct the cylinder portion will be $300 per square meters, while the cost for the hemisphere portion is higher, which is $400 per square meters. Now calculate the tank dimensions that will result in the lower dollars cost. So the tank have a certain volume. He gonna hold water of the amount of 500,000 liters, or in this case 500 cubic meters. Here the units are metric, so that's good for me, bad for you. Now how are you gonna build it with a lower cost? Like maybe we can reduce the hemisphere as much as possible and the cylindrical as big as possible, so that we reduce the amount of the money needed. In case you didn't imagine the shape, you are seeing a 2D style of the shape here, but I believe you can imagine it. Hopefully you can. So you got a cylinder, right? That's a cylinder. That's the center of the cylinder. Then you got here hemisphere, like half a circle, if you will. You know, I'm not sure if I made it worse or better, but yeah, so you have here hemisphere, you have here cylinder. This is $300 per square meters. This is $400 per meter square or square meters. Now you gotta do your calculations. Firstly, you need to have these set of equations governing the whole situation. So your theory in this case is, you use the theory that the other scientists developed previously, right? Volume of the cylinder, VC, equals pi r squared, which is the radius, by the height. Volume of the hemisphere equals 2 pi r cubed over 3. Surface area of the cylinder is 2 pi rh. Surface area of the hemisphere, 2 pi r squared. Now, assumptions, you assume that the tank contains no dead air space. Like the tank is ready to fill it totally. There's no air in it. Construction cost, depending on size. Concrete slab with hemisphere seal is provided for the base. Cost of the base does not change with the tank dimension. What you do, you find your total volume in meters as function of height and radius. Don't be confused about F of H and R, forget it. Now the volume of the tank, now they gave you the volume of the tank, right? What is the volume of the tank? VT would be 5 by 10 to the power of 5 or 500,000 liters. Now, we don't need liters. We need it in meter cube. We know that 1 meter cube equals 1,000 liters, right? Now, that means liter equals meter cube divided by 1,000. So here, if you divide by 1,000, that's going to give you what's the volume in meter cube, which would be 500 meter cube. Now, we know that the volume of the tank would equal the volume of the cylinder, which is area 1, and the volume of the hemisphere. So that would be VC plus VH. Now, what is VC? As you can see here, pi r squared h, and VH is 2 pi r cubed over 3. You can keep it that way. That's kind of your first equation. So VT is 500 equals pi r squared multiplied by h plus 2 pi r cubed, I believe, divide by 3. So that's your first equation. That's an equation. You can do nothing about it. Now we need to express the cost in dollars in terms of height and radius. So in this equation, radius and height are not defined. It's an equation of two factors. It's like x, y. Here, in this case, r and h. That's good. Now for the cost, I know the cost for the cylinder is 300 per meter square. What we're going to do for the whole cylinder, we're going to use the surface area of the whole cylinder. What's the surface area equation? SAC, 2 pi r multiplied by h, plus we know that for the hemisphere it's 400 per meter square, but we don't know how many meters square unless we use the surface area of the hemisphere equation, which is 2 pi r square. Hopefully you get that, doesn't confuse you. Okay, so you have here as well r and h, not defined, and c. Let's go to the next slide. So next you say you need to solve for h in equation 1, which would give you 500 over pi r cubed. Then after you solve for h, what you're going to do? You need to solve the cost equation by substituting h with whatever value it it includes. Oh, so for 1, we need to solve for h here. H would equal all of these guys. Without wasting your time, h would be, so from 1, h would be, as you can see in the slide, 500 divided by pi r squared minus 2r over 3. It's going to take you a while to reach here, but you can make it. Now we got h. We need to, let's see, this is equation 3. Now we say substitute 3 into whatever you see h, give it those values. See, that's a lot. I'm not going to type it in. H here, and that's it. That's the only h, actually. So when you do that, what you're going to get? You're going to get c to be in terms of r only. That would be, I believe, 300,000 divided by r plus 400 pi r squared. Now let's have a table. So we have cost and we have the radius. We can develop a table of cost versus radius. As you can see here, whenever we have cost and radius, so radius r, cost c. So when the radius is 1, plug in r in the equation, the value of c would be 300,000 roughly. For radius of 2, 155,000. 3, 4, 5, 6, 7, and so on. Then you look in the cost. Which one is the cheapest cost? Which one is the lowest cost? Which one is the cheapest? This one is the cheapest, so I choose r, the radius, to be 5 in this case. Now, if you choose the radius to be 5, then your cost c would be the substitution or the final value from 5. So in this case, I chose r to be 5. When I plug it in equation 3, substitute in 2, that gave me c to be $91,000. Now we can go back to equation 1, plug in r, then you find the value of h to be equal 3.033 meters. To verify, you can do differentiation in this case, but I wouldn't ask you for it in exam or homework or something else. Then 9, or the final result, you gotta, after you verify or check your results, you discuss or you conclude and write down your results and findings.